So chemical equations are an important aspect in chemistry, and so one of the important factors is balancing chemical equations. And so the goal is to determine the ratio of reactants, otherwise known as the starting material, to products. These are the end materials. And so we're going to do this by looking at or trying to analyze the ratio in which these things interact with one another. So when we have a chemical equation, if we were to write a generic equation, it might look like A plus B produces C, where A and B, these are going to be our reactants. And C is going to be our product. So in this chemical equation, if you were to slightly think about it, what we would notice is that it takes one molecule of A, that's seen over here, to interact with one molecule of B to create a single component of C. So in this case, in order to balance an equation, you have to look at the reactants and the products. So let's look at an example. So if we have N2O5 plus H2O produces HNO3. So the question becomes, is this equation balanced? Well, how on earth do we go about looking at that? So there are a couple of steps that we're going to look at in order to do this. So we'll solve this and then we'll write down the steps for us to look at in the future. So the first thing we want to do is figure out how much we started with in the first place. So I like to write down the elements that are present on both sides, N, O, and H. Now you could create a table or something else, but we want to total up how many nitrogens we see on the left side of our equation. So based on this, we only have 2. The number of oxygens is going to be a little bit trickier because we have to account for this oxygen and this oxygen. So we're going to end up with a total number of oxygens for 6. And the number of hydrogens we can see here, it's kind of an ugly color, but what we'll see is that there are just 2 of those. So if we analyze the right side of the equation, we have a single hydrogen, we have 3 oxygens, and we have 1 nitrogen. So as we look at this, our first idea is that these 2 sides are unbalanced. So we need to figure out how do we adjust both components. So the first thing we're going to look at is by adding a 2 right here. So if we were to add the 2, what does this change our values to? So now we have 2 hydrogens and 6 oxygens and 2 nitrogens. This set of values now matches this set of values. So now we have a balanced chemical equation. However, we've done some work, and the last thing we need to do is to rewrite our balanced chemical equation of N2O5 plus H2O yields 2HNO3. In the future, if there were states present, such as you might find here, you must include these. However, in the problem that we started with, there were no states, and so you don't need to develop those states. So one thing I like to think about is what we like to call a plan of attack. If you're given any chemical equation, how on earth do we start to think about this? So your first goal is to determine which elements are present on both sides. So once you do that, then you can start to look at, so how do we, if we figure out there's an imbalance, what do we do next? So if there is an imbalance, what you're going to do is start with one or a single element, modify that, modify using stoichiometric with stoichiometric values, then determine DET. Then determine, which values also changed. You might have to do this multiple times. So it may require multiple cycles. So your last step is to rewrite the balanced equation including any states. So let's look at another example. So in this case, we have sodium solid plus liquid water creates sodium hydroxide that is in the aqueous state. Oops, running out of space here. Which also gives off hydrogen gas. So we now see that we have states, which we're going to highlight in yellow. So these will need to be present in our final answer. So from here, we can actually go back and we're going to start the process of looking at what elements are present on each side. So we have sodium, we have hydrogen, and we have oxygen. One big trick or perspective here is to make sure that you write your elements in the same order. So if these three don't match, and I'm going to take these lines away in just a second, then you won't be able to directly compare the values. So we have a single sodium atom, 2 hydrogens, and 1 oxygen on the left side, or on the reactant side. On the product side, we have a single sodium. There are 3 hydrogens, and we have a single oxygen. I also made a small mistake here. And there is 1 oxygen. So what we can see is that what we're starting to note is that there are slight differentials here, but some, like the sodium, these are balanced, and the oxygen is also balanced. However, the hydrogens are unbalanced, and so the question becomes, what do we do? So we have to start somewhere. So the question becomes, what is the best thing to start with? In my opinion, it is unwise to begin with elements such as sodium or hydrogen gas. Because both of those have only 1 element, it will be easy to use those to finalize our values. So from here, I'm going to use, we need to balance the hydrogens. So in order to do that, I'm going to strategically look at the sodium hydroxide. And in order to do that, I'm going to put a 2 in front of that. Now, the reason I added a 2 is because I need to get the hydrogen values to be even, because we will always see a group of 2 here. So I added a 2 in front, which gives me 2 here. So let's go back and recalculate these values. So we now have 2 sodiums. We have 2 hydrogens in sodium hydroxide, plus 2 more, which is 4 here. And we have 2 oxygens. Now, when we go back to the other side of the equation, we're still quite unbalanced. These values do not match. So we're not yet complete. So now we can go back onto this side, and so we can see that the sodium needs to increase its stoichiometric component by 2. But the hydrogen, in order to have the same number of oxygens, needs to have a 2 in front of it. So let's put a 2 here, and then we're going to recalculate our elements. So we have 2 sodiums, we have 4 hydrogens, and 2 oxygens. So luckily enough, or not unlucky, because we use science, what we'll see is that these values are the same. And so now we are going to rewrite our chemical equation. We have 2 sodium solid. We've had a slight technical difficulty. So what we did is we rewrote our chemical equation, which has 2 sodium plus 2 H2Os creates these 2. So now let's try one on your own. So what we're going to try first is the one that looks a little bit like this. So we have Ba3N2 solid plus HF aqueous creates BaF2 aqueous plus NH3 liquid. So why don't you go ahead and set this on pause, and while you do that, you can go ahead and complete this on your own piece of paper, and when you come back, we'll talk about how you do it. Welcome back. Hopefully you used our plan of attack, where you looked at what elements were present on the reactant side and compared them to what we see on the product side, and then balanced your chemical equation. So first, what do we have? We have barium, nitrogen, hydrogen, and fluorine. So on the left side, we have 3 barium, 2 nitrogen, 1 hydrogen, 1 fluorine. On the product side, we have 1 barium, 2 fluorine, 1 nitrogen, and 3 hydrogen. So none of our starting material values are the same, but that's okay. So the question is, who do we start with? So I'm going to start by trying to balance the number of bariums. So I'm going to look at these 2. So in order to do that, I'm going to add a single 3 here, to where when we reconfigure this, we have 3 barium, and now we have 3 times 2 is 6 fluorine, okay? So the other thing involved in this over here is the nitrogen, and so there are 2 nitrogens here, and so I'm going to go ahead and add a 2 in front of the ammonia, and so there are now 2 nitrogens and 6 hydrogens. So when we compare these 2 values, we can see that the barium and the nitrogen match, so we have a good match here and here. However, the H and the F don't, but we're kind of lucky in the fact that if we add a 6 in front of the HF, we now have 6 hydrogens and 6 fluorine. So from here, we can go back and rebalance our chemical equation, where we have Ba3N2 solid plus 6HF aqueous yields 3BaF2 aqueous plus 2 NH3 liquid. Running out of a little bit of space on there. Sorry about that. So, shall we work a more complex example? So if we have one, and you guys can try this too. So now instead of having single elements, we are going to have all inorganic compounds. Whoops. So we're going to look at this one. Oops, typo, hang tight. Forgot some parentheses. So with our parentheses, we have platinum, NO2, 4. So we want to, why don't you guys try balancing this equation? So pause and try it. Welcome back. Hopefully this one was a little bit more challenging. So again, our plan of attack doesn't really change. So, but the biggest variation has to do with how we look at our components. So when we think about 10-nitrite, it actually breaks up into two parts. We have the nitrate component, which you can find the same component over here. And we can see our 10 here. And so the other components are single elements. So one of the things that we're going to do is instead of splitting out this nitrite molecule, we're going to leave it bundled together. We have a platinum and another nitrogen. So we have 110, there are 4 nitrites. We have 3 platinum and 4 of these nitrogen. So on the other side of the equation, so when we start to look at this, the question becomes, how do we balance this? So we know that the platinums are imbalanced. So let's start with those first. We're going to add a 3 here. So we are going to increase our platinum. 3 times 4 is going to be the nitrites. 12 of those and 3 platinum. On the other side of the equation, we need to balance the 10. So we're going to add a, come back here. Move it over a little, a 3 here. So from here, we're going to end up with 3 and 12. So now all of our chemical components are balanced, so we can rewrite our chemical equation. Sorry about that. So the thing that we looked at here was identifying the fact that the nitrate molecule seen here that I'm circling is observed both here and on the other side. So you can leave it together and it will make your balancing of equations easier. So let's do one last example that you can pause and predict. So if we have calcium carbonate, that's the wrong element, plus H3PO4 gives you calcium phosphate plus H2CO3. So why don't you guys pause and predict this one? Welcome back. So now we're going to do the same thing. But before you do anything on one that's this complicated, let's look at, with our highlighter, where we see components on both sides. So this carbonate molecule that I'm getting a green box, we can find here and here. So we can leave that all bundled together. We can also find the phosphate ion on both sides. So when we see the phosphate ions on both sides, it's going to simplify the quantities that we're going to explore. So we have calcium, we have carbonate, we have hydrogen, and we have phosphate. So when we look at all four of these groups, we're only going to balance four things because the blue boxes that we're looking at aren't going to change. So we can write down the same things on the other side. So let's write down how many of each we see. I'm going to start on the products. So we have 3 calciums, 1 carbonate, 2 hydrogen, 2 phosphate. On the reactant side, 1 calcium, 1 carbonate, 3 hydrogens, and 1 phosphate. So in this one, it looks a little bit more or less complicated. But I'm going to start by balancing the calciums and the phosphates. But I'm going to balance them on the side that has less. So we're going to add our values instead. Usually we've added them on the product. This time we're adding on the reactant side. So on the left, there is 3 calciums. So we need a 3 here. So now we have 3 calcium, 3 carbonates. There are 2 phosphates on the left, on the right side, so we're going to add a 2 here. So now we have 6 hydrogen and 2 phosphates. So this is great because now the calciums and the phosphates balance, but nothing else does. So, but maybe a single value can increase what we see on the product side. So if we're looking only at the H2CO3, we can add a 3 in front of that, which is going to balance. So now we have 3 carbonates and we have 6 hydrogens. So now we have a fully balanced chemical equation. So let's rewrite our balanced chemical equation. Sorry about that, didn't mean to move it off screen just yet. So we have 3 calcium carbonates plus 2 H3PO4 produces or creates Ca3PO42 plus 3 H2CO3. So balancing chemical equations can be quite scary at the beginning. However, if you take it apart and note that there are, at any given time, only 4 components, then these 4 items are easy to balance. One of the ways it gets really tricky is you'll note that there are oxygens in all of the reactants and products. Sometimes I've observed that people get lost if they break up the oxygens or combine them. And so it is easiest to balance chemical equations if you only break it into 4 parts.